For decades, scientists looked at one of Saturn's moons and saw nothing. A frozen, battered, geologically dead relic of the early solar system. They were wrong. Spectacularly, embarrassingly, magnificently wrong. And the story of how that mistake happened, and how it was finally corrected, is one of the most humbling and electrifying tales in the entire history of planetary science. Mimas is a small world, barely 400 kilometers across, orbiting Saturn at a distance of roughly 186,000 kilometers. It's the smallest known object in the solar system to have gravitationally collapsed itself into a sphere. And for most of its scientific history, that was about the most interesting thing anyone could say about it. It had a giant crater. It cleared a gap in Saturn's rings. It looked vaguely like the Death Star from Star Wars. And then, apparently, the conversation ended. Scientists filed Mimas away under inert icy satellite and moved on to more exciting targets: Titan, with its thick orange atmosphere, Enceladus, with its dramatic geysers, Europa, with its vast subsurface sea. Mimas sat in the corner of the solar system, cold and forgotten, wearing its ancient wounds like a badge of insignificance. But in 2024, everything changed. A study published in Nature Astronomy revealed that beneath Mimas's ancient, cratered, apparently inert surface lies a global liquid water ocean, one of the youngest, most unexpected, and most scientifically important bodies of water ever discovered in the solar system. A world we had written off as a geological corpse turned out to be secretly, silently, astonishingly alive. So the question isn't just what Mimas is. The question, the one that keeps planetary scientists up at night, is how did we get it so completely, utterly wrong? The answer begins not with Mimas itself, but with our assumptions. And the most dangerous assumption of all was the one that seemed the most obvious. When the Voyager probes swept past Saturn in 1980, they sent back the first close-up images of Mimas, and those images were immediately dominated by one feature: the Herschel crater. At 130 kilometers wide, this impact basin covers nearly one-third of the Moon's entire diameter. Scale that relationship to Earth, and you'd have a crater wider than the continent of Australia, with walls stretching more than 150 kilometers into the sky. Mount Everest, the tallest mountain on our planet, doesn't even reach 9 kilometers. The impact that created Herschel was so violent, so catastrophic, that shock waves raced through the Moon's interior and converged on the exact opposite side, the antipodal point, tearing the surface apart into a complex web of fractures and canyons. Simulations suggest that if the impactor had been even slightly larger, or moving marginally faster, Mimas would have shattered entirely. There would be no Moon. Just another ring of debris around Saturn. But here's where the assumption crept in. Because the Herschel crater is still there. Its walls stand 5 kilometers high. Its central peak rises up to 6 kilometers. After billions of years, this vast scar on the face of Mimas hasn't slumped, hasn't relaxed, hasn't been smoothed out by any geological process. And to planetary scientists, that meant only one thing. The ice beneath was rigid, immensely, uncompromisingly rigid. If there had been any warmth in Mimas's interior, any slushiness, any liquid layer, the crust would have deformed over time. The crater walls would have sagged, the ancient features would have been erased. But they weren't. They were perfectly, stubbornly preserved. And so the conclusion seemed ironclad. Mimas was frozen solid, inside and out, a geological fossil from the violent dawn of the solar system. It was a textbook case of using surface morphology to infer interior structure. It was logical, rigorous, and scientifically defensible. It was also wrong. The first crack in this assumption appeared not from any grand theoretical breakthrough, but from a thermal camera and a shape that no scientist expected to see on a planetary body. In 2010, NASA's Cassini spacecraft made a close pass of Mimas and aimed its composite infrared spectrometer at the surface to map how heat was distributed across the Moon. The expectation was simple: warmest near the equator where sunlight is most direct, cooling gradually towards the poles. What they got instead was Pac-Man. The thermal map showed a sharp, angular boundary on the Moon's leading hemisphere, a V-shaped region where temperatures plummeted to around -196 degrees Celsius, significantly colder than the surrounding surface sitting at a comparatively mild -181 degrees Celsius. The cold region was shaped exactly like the iconic 1980s arcade character, mouth open, facing forward. And crucially, when scientists examined Mimas' invisible light, there was nothing there. The surface looked completely uniform. No feature, no boundary, no difference whatsoever. The anomaly existed only in the infrared, invisible to ordinary observation, but blazingly obvious once you had the right instrument pointing in the right direction. This Pac-Man pattern turned out to have a real explanation, and it had nothing to do with Mimas' interior. Mimas orbits deep inside Saturn's radiation belts, constantly bombarded by high-energy electrons trapped in Saturn's powerful magnetic field. These electrons slam preferentially into the leading face of the Moon as it orbits, sintering the fluffy, powdery surface ice, welding the loose grains into hard-packed crystals. Hard ice has high thermal inertia. Like a dense rock left in the sun, it absorbs heat slowly and retains it longer. It stays cooler during the day and radiates heat at night. The trailing hemisphere, shielded from this electron bombardment, remains powdery and insulating. It heats up quickly in sunlight but holds nothing in the dark. The result is that strange arcade game thermal signature. Mystery solved. And since the explanation required nothing exotic from Mimas' interior, the scientific consensus didn't shift. Mimas was still frozen, still boring. The Pac-Man was just a clever party trick performed by surface physics. But this is precisely where the story gets interesting, because the very instrument and mission that closed one question was quietly, patiently gathering the data that would blow the entire framework apart. Cassini orbited Saturn for 13 years, from 2004 until its deliberate plunge into the planet's atmosphere in 2017. During that time, it didn't just photograph Mimas or map its surface temperature. It tracked the Moon's gravitational behavior with extraordinary precision. And buried within that data was something that didn't fit. Mimas was wobbling. The wobble in question is called libration, a slight rhythmic oscillation in a Moon's rotation as it orbits its planet. Think of it as the Moon rocking gently back and forth, a motion driven by the gravitational relationship between its shape, its interior structure, and its orbital dynamics. Every Moon experiences some degree of libration, but in 2014, when researchers carefully measured Mimas' libration using Cassini's tracking data, they found that the wobble was nearly twice as large as the models predicted for a completely solid body. There were two possible explanations. Either Mimas had a strangely elongated, rugby ball-shaped core that was creating an unusual gravitational signature, or the outer ice shell was physically decoupled from the interior, floating freely on top of a global liquid layer. Most scientists at the time chose the rugby ball. It was the simpler answer, and it required no exotic hidden ocean. The ancient, perfectly preserved Herschel crater was still sitting there, staring at them, daring them to suggest that anything warm or liquid could possibly be lurking underneath. And so the rugby ball hypothesis won the day, and Mimas stayed dead. What changed in 2024 was not new data. It was a more complete analysis of the data already in hand. A team led by Valerie Laney went back through the entire 13-year Cassini dataset and focused on a different measurement, the rate at which Mimas's orbit precesses. Because just as Mimas gravitationally shapes Saturn's rings, Saturn and the rings push back on Mimas, causing the elongated oval of its orbit to slowly rotate around the planet over time, like the hands of an extraordinarily slow clock. The rate of this precession is exquisitely sensitive to how mass is distributed inside the moon. And when the team ran the numbers, the rugby ball corps couldn't explain what they were seeing. The precession rate was wrong. The orbital drift was wrong. There was only one configuration of mass, one interior structure, one model that reproduced the observations exactly, a global subsurface ocean, lying beneath an ice shell between 20 and 30 kilometers thick. The ocean on Mimas is not like the ocean on Europa, which likely formed billions of years ago and has had eons to develop its chemistry. It's not like Enceladus's ocean, which is actively venting into space and has already been sampled, chemically, by Cassini's instruments. The ocean on Mimas is estimated to be between just 2 and 25 million years old. In cosmic terms, that is extraordinarily, almost incomprehensibly recent. The Herschel crater is ancient. It formed in the chaos of the early solar system billions of years ago. The ocean beneath it may have formed around the same time that our earliest human ancestors first walked across the African savanna. This is why the surface of Mimas still looks undisturbed. The heat of the ocean simply hasn't had time yet to work its way through that thick, insulating ice shell and reshape the world above it. This young age also resolves what scientists had long called the Mimas paradox, one of the most baffling inconsistencies in outer solar system science. Standard tidal heating models predict that Mimas, being closer to Saturn than Enceladus and having a more eccentric orbit, should experience more intense tidal flexing, more friction, more internal heat, more geological activity. Enceladus should be the quiet one. Mimas should be spraying geysers. Instead, everything appeared to be reversed. Enceladus was alive. Mimas was a corpse. The prevailing explanation was that Mimas had simply frozen solid early in its history, becoming too rigid to flex, too stiff to generate heat through friction, locked in a high dissipation state from which it could never escape. Enceladus had somehow stayed warm long enough to keep flexing, and so it kept producing heat. It was a plausible story. It was also, it turns out, incomplete. What the new models suggest is that Mimas's orbit wasn't always as it is today. Gravitational interactions with other Saturnian moons, possibly Tethys, possibly Dione, likely kicked Mimas into a more eccentric orbital path at some point in the geologically recent past. This increased eccentricity dramatically amplified the tidal forces squeezing and stretching the moon's interior. Friction built. Heat accumulated. And at some critical threshold, Mimas crossed the line from solid ice to liquid water, not gradually, not in slow increments over billions of years, but in what amounts, geologically speaking, to a sudden transformation. The paradox isn't that Mimas is cold. It's that Mimas is cold on the outside and secretly, silently extraordinary on the inside. It didn't miss its window. It simply hadn't opened it yet. This ocean will not last forever. The very process that created it is also slowly destroying its conditions. As the liquid interior sloshes with the tides, it dissipates energy, acting as a brake on the orbital eccentricity that powers the whole system. Slowly, the orbit will circularize. The tidal stretching will diminish. The heat source will fade, and when it does, the ocean will begin to refreeze. As water converts back to ice, it expands. That expansion will push outward against the crust, and the crust, already kilometers thick and under enormous stress, will crack. Massive canyons will tear across the surface of Mimas, transforming it into something that looks more like the scarred face of Charon or the fractured terrain of Dione. The world we see today, ancient, cratered, deceptively inert, will be destroyed. We are watching Mimas at the single most extraordinary moment in its entire existence, and we almost didn't notice. The story of how we got Mimas wrong is not a story about bad science. The instruments were precise, the logic was coherent, the reasoning was sound. It is a story about something more fundamental, the danger of letting a single piece of evidence anchor an entire conclusion. The Herschel crater was so visually overwhelming, so physically dominant, that it became the lens through which everything else was interpreted. It said, "frozen." And so frozen, Mimas remained in the scientific imagination, until a thermal camera drew a cartoon character on its surface, until a wobble appeared that was twice the expected size, until 13 years of gravitational tracking finally forced a reckoning with what the data had been trying to say all along. If Mimas can hide a global ocean beneath 20 kilometers of apparently inert, ancient ice, if a moon that looked this dead can turn out to be this alive, then every assumption we hold about every other quiet, cratered, seemingly unremarkable world in the outer solar system has to be re-examined. The moons of Uranus have been largely ignored, studied only by Voyager 2 in a single flyby in 1986. The objects of the Kuiper belt are distant and cold, and we assumed geologically irrelevant. But Mimas has just demonstrated, with humiliating clarity, that our assumptions about quiet worlds are not to be trusted. Liquid water, the foundational ingredient for life as we know it, may be hiding in places we never thought to look, wrapped in silence, beneath surfaces that told us nothing because we thought we already knew the answer. There is something profound and deeply human about this story. We saw a crater and called it a tombstone. We saw rigid ice and called it a dead end. We looked at a small, gray, battered moon and decided without fully listening to what it was telling us that there was nothing more to hear. And then, with patience and precision and the willingness to go back and question what we thought we knew, the universe whispered something extraordinary. Something it had been trying to tell us all along. Mimas is not a lesson in failure. It is a lesson in humility, and in the staggering, relentless creativity of the cosmos. Every world we have ever dismissed, every moon we have labeled as boring, every object we have filed away as understood, each one might be carrying a secret that our assumptions prevented us from seeing. The question isn't just what else we've gotten wrong. The question is, what are we getting wrong right now, today, about the very next world we've already decided isn't worth a second look? Because if Mimas has taught us anything, it's that the universe rewards the scientists brave enough to go back and ask again, and it saves its most astonishing answers for the places we least expected to find them.